Today we're going to take a look at BLAST and how BLAST calculates sequence alignment statistics. BLAST was developed to allow very fast searches through databases. The main criteria of BLAST was speed, so that it could search through GenBank. As we all know, GenBank is growing very quickly. It has to be sensitive. It needs to get most or all of the matches that are there. And it has to be specific. Hopefully the matches that it finds are the correct ones. So there are several types of BLAST. If you're using a DNA query and a DNA database, you use BLAST-N. If you're using a protein query and a protein database, you use BLAST-P. Those are the two quickest searches. If you've got nucleotides compared to proteins or proteins compared to nucleotides, you can translate those nucleotides and do either T-BLAST-N or BLAST-X comparisons. And finally, if you want to compare DNA sequences at the protein level, you can do a T-BLAST-X search. BLAST is what's called a heuristic. That means it makes some assumptions about what you're looking for. It assumes that two sequences are similar if they have a word in common. These two DNA sequences share a 6-letter word that's in common, CAG, AGC. It's in both sequences. However, these two sequences don't share any words in common. Which of these sequences is the more similar? The one on the right actually has 8 bases that are identical between the two sequences, and the one on the left only has 6 bases that are identical. So BLAST may miss a case like the one on the right and may report a case like the one on the left. The heuristics were introduced to make BLAST work very quickly, and that's the trade-off that you get when you want to search through millions or billions of sequences and have the results returned to you in just a few seconds. The way the algorithm works is that it finds all the possible words in the query and it scans the database for the occurrence of those words. And then we score the search using a matrix. So we start with an amino acid sequence like this one shown here, and we find all possible words. We're going to use 3-letter words like LIA, IAW, AWH. Notice that we're finding all of them and that they overlap. We use our scoring matrix, like our PAM matrix or a Blossom matrix that we've talked about in other lessons, to score these individual sequences. What would be the best score that they could accomplish? Of course, from a scoring matrix, the best score is always on the diagonal line of an amino acid to itself. And so what's the best score that these individual words could achieve? If we have LIA, L to L would give us 4, I to I would give us 4, and A to A would give us 4. The total for this word, in the best possible case, would be 12. For WHC, the individual components are shown, and the total score that WHC could achieve would be 28. And we can scan all of the words that we construct from this amino acid sequence for the best possible score that they can achieve. We filter out those words that are below some particular threshold. You can specify this as a BLAST option. But basically this is just a way of removing uninformative parts of the sequence that aren't going to be very useful in searching through a database. They're going to occur a lot of times. And now that we've got our words that are highly informative, we can scan for them, and we can start scoring our alignment. We extend the score if the threshold is above a certain value. Again, you can set that using the -F option, and we try and extend in both directions. If we can't extend, we try and join with gaps. Once we've extended as far as we possibly can, we end up with what's called a high scoring pair, or HSP. And we use our protein substitution matrix to score that HSP. The alignment has an I and an L, that gets a score of 2, an I and an I, that gets a score of 4, an A and an A, that gets a score of a 4, and so on. We have one gap insertion, and so we have a gap opening penalty and a gap extension penalty, and these both get a score of -2. And so our total score for this alignment is 54. Notice that the score is a property of the alignment and the substitution matrix that we're using. That score will never change. As long as we use the same matrix and we result in the same alignment, we'll always end up with a score of 54. Now we can change our parameters, in which case we have to do everything again. But our raw score is only dependent on the parameters that we start with and the alignment. So what does the score of 54 mean? The score is 54. That's the raw score. It never changes. But we want to know, is it a real hit? Or is it a significant hit? Significant compared to what? So we start with a pairwise score and we try and calculate whether it's significant. The way that we do this is we start with our protein sequence and we calculate all possible combinations of those amino acids in random. So these are just a few of our choices. They have exactly the same amino acids, but we've just jumbled up the order. We calculate all the possible sequences, and we align all of those sequences to our database sequence that we found and that from which we calculated our score. You can see here I've aligned some of them and I've calculated the scores for those alignments. All of these sequences derived from the same amino acid string as our query, but they've all been organized just in random. So we plot those scores on a chart. We plot the score on the x-axis and the number of alignments on the y-axis, and we get a curve like this. We lay on this our score of 54. That was our raw score from our sequence. We can get back the probability that this alignment is random. The fraction of random sequences with a score greater than 54 gives us the likelihood that our alignment was just at random. If that fraction is very low, it means that our score is significant. If that fraction is very high, it means that there's just a good chance that our alignment was just one of those random ones that we've chosen. So this is a very trivial calculation to do for any sequence, and in fact you can pre-calculate that based on the composition of your particular sequence. So for probability, here's some good rules of thumb. If you get a probability of 10 to the minus 100, it means that you have identical sequences. Between between 10 to the minus 50 and 10 to the minus 100, you have nearly identical sequences. From 10 to the minus 5 to 10 to the minus 50, you would describe those sequences as homologous. From 10 to the minus 1 to 10 to the minus 5, you would say that those sequences are distantly homologous. And a probability greater than 10 to the minus 1 would suggest that your sequences might be random. This is for probability. These are only rules of thumb, and you're welcome to make up your own definitions for these words or other words based on your experience with sequence alignment. BLAST is more complex than I've shown you because there's a lot of problems with sampling and the statistics that we have to figure out. Another problem that we'll run into is that longer sequences are more likely to find higher scoring pairs because they're longer. And longer databases are more likely to result in higher scoring pairs because they're longer. And so one of the considerations that BLAST came up with was that we wanted to convert p-values, probability values, into expectation values or e-values. The idea is, what's the expected frequency that we would find this alignment in the database just at random? The e-value is basically the length of the database multiplied by the length of the sequence multiplied by the probability. In fact, we can describe the e-value as k times the length of the database times the length of the query sequence multiplied by e to the negative lambda s. S is the raw score, 54 in our case. K and lambda are just scaling factors that you can define as parameters to BLAST, and if you look at the end of a full BLAST output, it will actually tell you exactly what K and lambda are. The scaling factors to get from the raw score, the length of the database, and the length of the protein to an expect value, an e-value. We can also convert the raw score to what's called a bit score. Since K and lambda are scaling factors, we can basically just eliminate the scaling factors, and S prime here is our bit score, kind of like the amount of information that's carried in our sequence. We can go from a bit score to an e-value, still remembering that the e-value is dependent upon the length of the protein and the length of the database. As the database grows, all databases grow, as the database grows, the e-values will change. An important relationship here is that the higher the bit score, the lower the e-value. And so for e-values, we talk about less than 10 to the minus 100 being identical, 10 to the minus 50 to 10 to the minus 100 nearly identical, 10 to the minus 5 to 10 to the minus 50 being homologous, 10 to the minus 1 to 10 to the minus 5 being distantly homologous, and greater than 10 to the minus 1 being random for e-values. Let's take a look at a DNA sequence alignment. Using T-BLAST-X, we've aligned these two apparently unsimilar DNA sequences. There's 12 bases here, and so our DNA score, if we just scored +1 for a match and -1 for a mismatch, would have a score of 12. However, each of these codons encodes for the amino acid proline, and a proline to proline match gets a score of 7. So we would have a raw score for this alignment of 28. But you can see that one of our sequences just has long runs of C's, and that may not be a real sequence. And so one of the things that BLAST introduced is filtering. The idea is that we want to remove low complexity sequences like that long run of C's that I just showed you. We don't want to seed, we don't want to start looking in low complexity regions, and we should not extend through low complexity regions. But we don't necessarily have to change the length of our sequence to do that. An alternative way to do it is to convert the low complexity regions to n, and that will actually change the sequence and ignore them completely. And because we've changed the sequence, we've changed the length, and we'll change the e value. So ignoring them is called soft filtering, and changing the sequence is called hard filtering. There's two low complexity filters that come standard with BLAST. Seg is used for proteins, and DUST is used for nucleotides. But there are also other commonly used low complexity filters like repeat masker or SWAT that you can find online. Notice, however, for some applications you may want to turn off filtering. It may not be what you need. And then finally, just a comment about position weight matrices. Position weight matrices start with amino acid alignment, like this one, and we score each position. So in the first position, there's a D or an E. In the second position, we have an R, a K, or an E. In the third position, we have an S or a T, and so on and so forth. And so we can score our alignment, and we can score a new alignment by looking at how its amino acids match up with our matrix. Our first position in our new sequence is an E, and so that has a probability of 0.4. Our second position is an R, and that has a probability of 0.2. Our third position is an S, and that has a probability of 0.8, and so on and so forth. And we score each of the positions in our new query sequence based on the scores that we got from our amino acid alignment. So we get a total score where we just sum up all of the positions and divide by the length of the sequence, and that gives us a value that suggests whether or not our new sequence is related to those ones we already know about. So Psi-BLAST has a built-in algorithm for calculating position-specific matrices. You start with a regular BLAST, and that generates an alignment. From that alignment, you build a position-specific matrix. From that position-specific matrix, you can scan proteins for significant matches that may not appear purely based upon sequence composition. Using Psi-BLAST, you're not just relying on your single query sequence, but you're bringing in information from the other sequences that are related to your query sequence. Psi-BLAST is very good for finding distantly related matches in proteins that have evolved from each other. So what I've told you today is that there are different flavors of BLAST for proteins and nucleotides, and that the raw score does never change. The raw score is just from the alignment and the parameters of the algorithm. E-value depends on the size of the database. If your database changes, your E-value will change. If your database changes, you cannot just take BLAST results from the previous version of the database and compare them to BLAST results of a new version of the database just using e-value. You have to recalculate the e-values because they've changed. And I've also told you that filtering may be good in some circumstances as it removes some of the low complexity regions of your sequence, but you may also want to consider switching off filtering in some circumstances when you don't want to eliminate those sequences.